we've seen lots of examples of parametric curves, but parametric surfaces, but maybe we should talk about something we can actually calculate with parametric surfaces. I mean, if you have a surface, you might want to know what is the area of that surface. For simple surfaces like planes or surfaces of rotation, if you're rotating the graph of a function of where y is a function of x, right, this sort of surface, right, there are sort of Calc 1 tricks that you can use to figure out, or Calc 2 tricks you can use to figure out the area of this kind of thing. But parametric surfaces can really take on any shape, not just these sort of simple shapes. And so it's a harder problem to figure out to figure out an integral you can write down to get the area of a parametric surface. So what we need to do is figure out, so we have this patch in the UV plane that R situates in the R situates as a parametric surface in the in XYZ space. What we need to do is figure out at every point in the domain over in UV space, what is the little patch of area at that point on the surface, right? Okay, well, what we can do is we can actually use an idea very similar to what we did when we figured out how to change coordinates in a double or triple integral. What we can do is change u a little bit by an amount du. That causes a corresponding change over in the over on the surface. We might call this delta u. So what is delta u? Well, remember how this worked out. How this worked out when we were doing substitutions is you take your coordinate functions and you just take their derivatives with respect to the variable that you changed. So if we take this parametric surface and take its derivative with respect to the variable we changed, that's partial r partial u, so times du, right? Now this is a vector. Okay, so when we did this for a change of variables for a triple integral, we would have written this partial x partial u, comma, partial x partial partial y partial v, sorry, partial y partial u, comma, partial z partial u. But right, x, y, and z, that's just our, in this context, x, y, and z are just the coordinate functions for our parametric surface. So this partial derivative is just a nice way to package up this vector of scalar partial derivatives. Okay, so that's just the u direction. Now if we change v a little bit by an amount dv, that causes a change in our position over on the surface, and that change, we could call that delta v, and we would write that partial r partial v times dv. Okay, and then these two vectors, right, they bound this little patch of area, and we need to know how much area is in this little patch. Well, we're very fortunate again because we're asking for the area of a little parallelogram that's bound by two vectors. So the area of that little parallelogram is the magnitude of the cross product of these two vectors. So magnitude of delta v cross delta u cross delta v. The order of the cross product doesn't matter since we're taking a magnitude. And this is magnitude of, so partial r partial v, sorry, let me do partial r partial u first, cross, okay, now partial r partial v. And these differentials du and dv, they act like scalars, so we can move them outside of the magnitude, du dv. Okay, so this is the area at one point. If we want to know the total area, well, we just need to integrate over the entire region D over in our parameter space. So the area of the entire surface is the double integral over our domain in the parameter space of the magnitude of partial r partial u cross partial r partial v du dv, or dv du, right? The order doesn't matter. So this quantity that we're integrating, we could call this is the differential of the surface area, right? If integrating it gives you the total area, then this thing we integrated must be the differential of the total area. Different people use different symbols for this, but I think what we will use is a lowercase sigma. That's one of the common symbols that people use for this quantity right here. So what we found is a formula for the infinitely small patch of area at each point, and it's d sigma, this cross product, times du dv. All right, let's actually calculate one of these. Let's double check that this calculation seems to be working by doing an example where we already know what the answer should be, and just make sure that this calculation does produce the answer we think we ought to get. So let's find the surface area of a sphere with radius capital R. Now we know what the surface area should be, sort of from classic Greek geometry. It's 4 pi times the radius squared, right? So let's see if we can get this out of our formula. So let's calculate partial r partial u. Actually, partial r partial theta. I'm using theta and phi here. So partial r partial theta. That's going to be minus r sine theta sine phi, comma, r cosine theta sine phi, comma, 0. There aren't any thetas in the third coordinate. And then partial r partial phi is going to be r cosine theta sine phi, comma, r sine theta cosine phi. I need a cosine here, not a sine. I failed to take a derivative. Okay, comma, minus r sine phi. Okay. All right, now we need the magnitude of the cross product of this. And this calculating the magnitude of this cross product is not difficult, but it is kind of a grind. If you've used the change of variables formula to get the volume element for spherical coordinates, then you've actually essentially already done this calculation. So I won't drag you through it, but it turns out what you get is capital R squared times sine of phi. Okay, which hopefully doesn't come as too much of a surprise that this looks familiar. So now let's calculate the area of the sphere by integrating this thing. So what we're going to integrate is d sigma, so that's this magnitude r squared sine phi d theta d phi. And to cover the whole sphere, phi has to go from 0 to pi, and theta has to go from 0 to 2 pi. Okay, so we can separate these. We can move the r squared all the way outside because it's constant. The phi integral is the integral of sine of phi d phi from 0 to pi. And the theta integral is the integral from 0 to 2 pi of just d theta. Okay. So this is r squared times integral of sine is minus cosine phi from 0 to pi. And the integral of d theta is theta from 0 to 2 pi. So r squared times. So you have to be careful with all of your plus and minus signs when you're plugging in these bounds. But if you account for all the minus signs, right, cosine of pi is minus 1 with another minus, that's plus 1. And now when we're plugging in the bottom bound, we get minus cosine of 0, so that's minus 1. Okay, and then for theta, we get 2 pi minus 0. So this is r squared times 2 times 2 pi. And yes, indeed, as we expected, that is 4 pi r squared. So our formula for the area of a parametric surface does appear to be working.